Hello, good afternoon, everyone. Can you hear me? Yes, okay, thank you. Okay, let's continue on our lecture. So I think last week we learned about the first law of thermodynamics, which is conservation of energy. Energy cannot be created or destroyed. And we have the first law efficiency, which is based on the general equation of the efficiency that we know output over input. Okay. And then we also have another one called second law of efficiency. Sorry, second law of thermodynamics. So in this second law of thermodynamics, it states that the total entropy of an isolated system always increase over time or remain constant in reversible process. Entropy here refers to the disorderly in the molecule disorderly of the substance. Okay, so it means that this entropy you are getting higher for the isolated system. Isolated system is mean that there's no heat transfer in or out. Okay, why it will become higher? So we can look in this way. This is a better explanation on the what's mean by second law of thermodynamics. Entropy, we can refer it as a disorderly. Okay, you can see that in the first stage, this is the blue and red maybe molecule. They're separated into two different tanks. Okay, once I remove the separator, you can see that when the time progresses, blue and red molecule will mix together. Definitely, it will go toward equivalent as its own. Similarly, you mix two color of liquid together. Okay, so eventually they will mix together. Okay, and this is why we say that the entropy of the isolated system always increase. You don't need to give any energy for the entropy to increase. Okay, similar to your maybe we can talk about the environment, room or what. Let's say in your bedroom, if you do not do any work to clean it, to organize it, what happened to your room? You're getting more dirty and more dirty. Okay, it will be getting not organized, okay, and getting worse. And this is what we call as an entropy will always increase if you are not really do some work to improve it. Okay, so this second law of thermodynamics state that entropy of an isolated system always increase over time and may remain constant in the reversible process. It can remain constant, which you have a reversible process, or maybe it's not affected by anything. It will just stay constant. It's still possible. Okay. The increase in the entropy account for the irreversibility. You increase the entropy, you will reduce the capability to do work. It's because something like the molecule inside will have a difficulty to move. We can understand that way. Okay, now everything is random so that the molecule is very difficult to move. The entropy of any isolated system never decreases. It never decreases unless you add in the energy. Okay, that's why we always state that this term isolated system. You cannot say that the entropy of any system never decreases. That's wrong. As long as you add in the energy, it can improve. Okay, but if you don't add in the energy, which is the isolated system, then entropy will never decrease. An isolated system evolved toward thermodynamic equivalent, the state of maximum entropy of the system. Okay, can be thermodynamic equivalent or any kind of equivalent. We also can say it as a maximum entropy. Everyone mix evenly. Okay, this is what we call as a maximum entropy. Okay, then we also have one law. We have law for this. We have efficiency for second law, which measure the performance of the device relative to the performance under reversible condition for the same end stage as given by this. And two, the two here refer to second law, okay, equal to NTH thermal efficiency for the first law divided by NTH REB thermal efficiency for the first law in reversible manner. Okay, so in the layman term, we can say that first law efficiency is actually output over input. How much you get divided by how much you put in into the system. Okay, and this second law efficiency is how much you get over how much maximum possible you will get. Can you see the difference? You don't care about input anymore, but we care about maximum possible output. We take that as a reference, okay, and then we calculate the second law efficiency. Okay, so the second law efficiency tells us how much we get out compared to the maximum possible we could get out, given the inlet and exit condition. So is first law is output over input. Second law is output over maximum possible output. Okay, so we can foresee that the second law efficiency should give you a better value most of the case. Let's try this example. A heat engine receives a heat from the source at 1200 Kelvin at the rate of 500 kilojoule per second. Kilojoule per second here refers to kilowatt, and reject the waste heat to the medium at 300 Kelvin. The power output of the heat engine is 118 kilowatt. Determine the reversible power and the irreversibility rate of this process. Okay, so first, this 180 kilowatt is the actual output. Okay, this is the actual output. This is input. So I say that input is equal to 500 kilowatt, and output is only 180 kilowatt. Okay, if you want to calculate the efficiency, thermal efficiency, you'll get 180 divided by 500. This is the first law efficiency. But if you need to calculate the second law efficiency, then you need to see what is the maximum possible output of this 500 kilowatt. Okay, then to know the maximum possible output, we also can refer to the Exergy. And the Exergy must take care of the environment condition, which is 300 Kelvin. So that this 1200 Kelvin will never drop to 0 Kelvin. Okay, so you only able to produce 500 kilowatt if this energy 1200 Kelvin of heat is totally released, which is dropped to 0 Kelvin. But we know that's not possible because the environment is 300 Kelvin. Okay, so the maximum possible temperature drop is only 900 Kelvin. So from here, we can get the thermal efficiency at reversible condition, which is 1 minus 0 minus divided by T height, which is 1 minus 300,002. And this is our reversible thermal efficiency. Okay, so 3 divided by 12, you get 0.25. So we have the efficiency of 75%. And based on these, we can calculate what is the maximum possible output. Out of 500 kilowatt, only 75% can be converted to useful work, to actual output. Sorry, maximum possible output. Okay, so we can get reversible output equal to 500 kilowatt multiplied with 0.75. And this we also call it as a maximum possible output. So I get 375 kilowatt. Okay, so it means that if you calculate just the efficiency, it will be 36%. Okay, and if it is a reversible process, the efficiency will be 75%. So based on the efficiency for reversible process, we can calculate the reversible output, which is 375. So it means that out of 500 kilowatt, the maximum possible output you can release is only 375. So based on this 375, we can calculate the second law efficiency. Okay, N2 equal to efficiency of the first law over efficiency of the reversible. Or you also can take the power output, actual power output, 880 kilowatt, divided by the maximum possible power output, which is 375 kilowatt. Okay. So the question asks to determine the reversible power. Reversible power is 375. Okay, and this is the second law efficiency where we can get 48%. Okay, and then the irreversibility rate for this process. Irreversibility rate is mean that how much power losses. So losses is, you can see, from 375, you only get 180. So the losses is, so equal to 375 minus 180. So the irreversibility loss is 195 kilowatt. Okay, I know that you may a bit blur because now you have too many efficiency. You have the first law efficiency, or we call it as a thermal efficiency. We have the thermal efficiency at reversible condition. You have the second law efficiency. So you need to be able to differentiate these three kinds of the efficiency. Okay, any question until this point? The question itself is not important, but you need to understand the concept of these three types of efficiency. Can follow on? Then I just move forward. Then after the first law efficiency and second law efficiency, now we need to calculate the exergy of a complete system. The complete system here can be a closed system, can be a flow system. Closed system is something like you have a fixed mass and there's no flow, something like a piston. Okay, you do not have flow continuously. And the flow system is something like compressor lah, nozzle lah, pump lah, all is considered as a flow system. You can see that the fluid inside is flow continuously, or turbine lah. Okay, these all are flow system, and closed system mostly refer to the piston. Piston in your car engine is called closed system. Okay, so to measure the exergy of the closed system, this is what we need to consider. The first, the change of internal energy. We need to consider a few types of the exergy. The first one is a change of internal energy. And there's only thing will change the internal energy, which is the temperature. You increase in temperature, it means that you increase in the internal energy. For example, if you are going to calculate the internal energy of the water, we use MC delta T. Okay, M is a mass, T and C is the specific heat capacity of the water, and T is the temperature. So MCT, you get the internal energy. MC delta T, you get the change in internal energy. And we can represent the internal energy as U. And in terms of internal energy, we also have two types. One is called sensible heat, and one is called latent heat. Sensible heat is one you can sense it. Okay, so it means that it's the heat absorbed when the temperature increase with no phase change, no change from liquid to gas, gas to solid to liquid, something like this. Okay, so this is when you, let's say for you heat up the water from 30 degree to 60 degree. Okay, so the internal energy will increase because of the temperature increase. Okay, and next thing we have the latent heat. Latent heat is something like hidden. We call it the hidden heat because you cannot see the temperature. The temperature will not change for this latent heat. This is the heat, the energy absorbed or released when the substance have a phase change. It can change from liquid to gas or gas to liquid. So when it changes to gas to liquid, it means that it will release the energy. It changes to liquid to gas need more energy, so it will absorb the energy. And that will not involve any change in temperature. Something like you boil the water. The water temperature is 100 degrees Celsius, and you keep boiling. The water temperature still remain 100 degrees Celsius, but it will change to gas, and it will change to steam. And then the steam will still remain at the 100 degrees Celsius. So it changes the phase, but not change the temperature, but it still absorb the energy. Okay, so this is we call it latent internal energy. But this is just for the understanding. When we do the calculation, we can always follow the steam table, follow the ideal gas law. Okay, and this exergy can be transferred across the boundary only when the temperature difference exists. And the closed system exergy is given in this way: 1, 2, 3, 4, 5. Can you see that we have 5 terms over here? So exergy of a closed system can be represented with the symbol 5. This one really is 5. Okay, the first term, U minus U0. U0, because we are calculating the exergy, so we cannot just use the U. U will refer to the internal energy. But how much the internal energy can be released to the surrounding, can be used to do work, depends on the surrounding internal energy or surrounding temperature. So you have to consider U and U0. How much will left after you get the equivalent condition with the surrounding. Okay, so U minus U0. U0 is when the substance raise the temperature of the surrounding. How much is left? Okay, so we calculate the exergy, but not energy. If you calculate the energy, we just consider U. You don't need to minus U0. Okay, so we can see that we have U0, P0, V0, T0, S0. All with the 0 is referred to the environment or surrounding. Okay, so the first term is a change of internal energy. Okay, this one is the internal energy. The second term, if you still remember, P0 is the environment pressure, and this is a change in volume. Okay, so this one is a work done to the surrounding. Okay, so it means that you press against the piston. Sorry, you want to press the piston, you need to against the surrounding pressure. Okay, so it's work done to the surrounding. And then the third one is the irreversibility. Okay, and then S minus S0, S refer to the entropy. Okay, entropy refer to the disorderly lah. Okay, and then T0 refer to the environment temperature and must be in Kelvin. Okay, the unit must be in Kelvin. And do notice that this is a negative sign. So it means that this is not the amount of work we can use, but it's refer to amount of work we must lose. Irreversibility, when you have this process, to change from this state to this state, this is the amount of irreversibility that we cannot run off. This a condition of the substance. Okay, and the next is V squared over 2. This is the kinetic energy. And then the last one, G over H. G over J is the potential energy. So whenever we consider the total exergy of a closed system, these are the 5 terms that you need to calculate. First, change of internal energy. Second, work done to the surrounding. Third, irreversibility. And fourth, kinetic energy and potential energy. Okay, kinetic energy here, because this is a closed system, it means that the fluid or substance inside the system is not flowing. Okay, but the entire system may have the motion. Maybe the entire piston is moving at a very high speed. Something like you have an engine. Okay, and then the piston is inside the engine. Then your car is move at 100 km per hour. So you should consider that the system have the kinetic energy. Okay, and also the potential energy as well. And this is the exergy of the closed system. No question? Okay, then we move to the next one. Next, we calculate the exergy change. This is exergy, and this is change of exergy. What's the difference? When we measure the exergy, we will consider the amount of energy you can release from the initial stage U to the that stage, which is the surrounding condition. Okay, so it means that you have to release. Okay, maybe I like this. Exergy refer to calculation of the maximum possible power output. So it means that you will consider release of 100% of exergy you have. But for this one, we are going to measure the exergy change between two stages, from stage 1 to stage 2. Okay, maybe we can explain this way. Let's say this is time, and then this is the power. Okay, so at the beginning of the process, the temperature difference between the substance and the surrounding is very huge. Maybe we have a water. Inside is 100 degrees Celsius. Outside is 25 degrees Celsius. So at the beginning of the process, okay, on the very beginning, when you put this 100 degrees Celsius of water exposed to the environment, the temperature difference is 75 degrees Celsius. So what happened? The temperature will drop very fast. Okay, so you can see a big drop in the power. Okay, because the temperature will refer to the power released to the environment. So if you calculate the power output, it will be very fast because the heat transfer rate is very fast. But what if the temperature up to now it dropped from 100 to 26 degrees Celsius? Yes, it still have 1 degree Celsius to drop to 25, but the rate of heat transfer will be relatively less. Okay, from 100 to 50 is very fast. From 50 to 25 will be very, very low, very, very slow. Okay, it take longer time, and the heat released per unit second, per unit time will also lesser. So in that case, the power output of the system will be lesser. So most of the case, we will not wait the substance or the steam to drop until that state of 0. But we will stop at somewhere. Okay, maybe this is the heat transfer rate. At the beginning, very fast. At the end, very low. So maybe at this point is 100 watt. This point is 500 watt. Okay, and at the end, it will drop to 0, the heat transfer rate. Maybe our system need at least 100 watt to power. Okay, so I won't run my process to the end of the stage. This is the state 1, when the water is very hot. Okay, and this will be the state 2, end stage. I will stop my process over here. I won't use the energy at the back. The reason is the heat transfer rate is too low. Okay, so we always need to measure the exergy change instead of the total exergy you have. Both are important. This is to measure of the maximum possible power output. This exergy change is to measure maximum possible output at the given rate. Okay, in the process. So this is more on the process. This is more on the entire system. We don't care about the process. Okay, can differentiate. One is exergy change, not until the end, and then this one is just the total exergy you have. So you have to calculate until 0. Then you see what's the difference. So first, we can put this exergy change as an x. Because of the exergy change, okay, this one, we don't put x, we put 5. And this have the unit of kilojoule per kg. But for this case, if you need to calculate the exact exergy change, you need to multiply with the with the mass m. Okay, you can see that M multiplied with phi 2 minus phi 1. So this is the exergy you have at the final stage and minus exergy you have in the initial stage. Okay, and then same thing. This is the change of internal energy, work done to the surrounding, and this is the irreversibility. And the potential energy and potential energy and kinetic energy, mostly it will be ignored if there's no change from beginning and to the end stage. Okay, so this we call it as a exergy change. Then we move to the next one, flow energy. Okay, yeah. So just refresh a bit. For exergy of a closed system, we have 5 terms: change of internal energy, change of work done to the surrounding, irreversibility, kinetic energy, and potential energy. And then now we have the open system, or we call it as a flow system. The difference between flow system and the closed system is you will have extra energy, which called as a flow energy. This flow energy is the energy of is the excess of flow work done against atmospheric air at P0 to replace it by the volume. So it means that you need to push away the atmospheric air. The energy is needed. Okay, so we call it as flow energy. And the equation is very similar to the work done to the surrounding. You can see work done to the surrounding is P0, V2 minus V1, or V minus V0. But this one is P minus P0 multiplied with the V. V refer to the volume. Okay, but of course, whenever you have flow energy, we will not have the work done to the surrounding. Whenever we have the work done to the surrounding, we do not have the flow energy. The reason is simple. When you have the piston, the flow definitely, you definitely will not have flow because piston block the movement. Okay, block the flow. But the piston have to work against the surrounding atmospheric pressure. Okay, so that it means that when you have a flow system, you have to consider the flow energy. When you have a closed system, you have to consider the work done to the surrounding. And this is the complete equation for the exergy of the flow system. You can see that first one, I change of internal energy, work done to the surrounding, irreversibility, kinetic energy, potential energy, and flow energy. Okay, we add in the flow energy because now you have the flow. And then we throw away the work done to the surrounding. As we know that when you have the flow, there is no work done to the surrounding. No piston, you don't need to push against the atmospheric. But now you have the flow. The flow will push against the atmospheric. And then you can move this flow energy and combine with the change of internal energy. And this will give you the term of H. We call it as a enthalpy. Okay. So why do you want to do it like this? Just to make it easy to do the calculation. Okay, so we have new terms called enthalpy, where you include the flow energy into the internal energy. Okay, and then equation will now become simple. Enthalpy, change of enthalpy minus irreversibility plus plus change of kinetic energy and plus change of potential energy. You can see no more change of no more work done to the surrounding. Okay, so that for this, why you need to separate, it means that in the exam you need to separate, you need to identify the system is flow or non-flow. Okay, and then the exergy change of the flow system can be written in this way: H2 minus H1 from state 2 to state 1 for enthalpy, which is including the internal energy and flow energy. And secondly, is the irreversibility. Third, change of kinetic energy. And last one is the change of potential energy. And you can denote the flow exergy as psi. Remember, previously for non-flow is this phi, fully closed. But now it's open. Okay, phi and psi. Okay, so again, if you see this, the unit will be in terms of kilojoule per kg as well. But now the problem is, how are we going to find the enthalpy? You can see that this temperature, okay, temperature maybe you can easily get it, and velocity, height, gravitational force, I think okay. But where to get the enthalpy and entropy? Okay, so in general, we have two different types of substance. One we call it as a steam. Steam is very widely used because when we calculate the exergy, mostly refer to the steam turbine. Okay, you boil the water, produce the steam, and then steam go through a turbine and then give you the power. Okay, so first is the steam. But the problem of the steam is a non-linear substance. The pressure and temperature change is in the non-linear way. We cannot have one equation to represent the change of the pressure accordingly to temperature. We cannot say, the temperature is 100 degrees Celsius. What is the pressure? The temperature is 150. What is the pressure? We cannot estimate that way because it have the non-linear relationship. That's why to get the properties of the steam, we have to use the steam table. Okay, I will teach you how to use the steam table later. So based on the steam table, you're able to get the value for the enthalpy and also the entropy. This is what you will get from the steam table. And second substance that we will study is ideal gas. Ideal gas refers to that pressure, volume, and temperature will change accordingly to a standard law. We call it as the ideal gas law. And they have a linear relationship to each other. So that we can always use a simple equation and then to find the enthalpy and entropy based on the ideal gas law. Okay, what is ideal gas? None of the gas in the world is ideal gas, but the air, the nitrogen, the oxygen, okay, can consider as very close to the ideal gas. The properties is very close to the ideal gas. So you always can assume this kind of gas as an ideal gas, as something like a inert gas. You also can consider it as an ideal gas. Okay, so there are only these two things we can do, steam and ideal gas. Of course, you still have other non-linear substance that in the world, something like a coolant. Maybe coolant you use in the air conditioning system, maybe liquid or gases, ammonia. This kind of things also have the non-linear relationship between the pressure and temperature, but it's not very widely used. Only for maybe cooling system, we need a coolant. And coolant also have many types, not only one type. Okay, so mainly we focus on steam and ideal gas in the syllabus. Okay, then let's talk about the ideal gas law. Ideal gas law is very simple. PV equal to nRT. P refers to the pressure, V is the volume, and N is a mass, T is the temperature. And these have the one static or one constant relationship with the R. R refers to just a constant. Okay, just a multiplication to make this equation the same as the from both sides. R. Okay, so what you need to use for P, V, M, and T, you have to refer to the unit given by the R. You can see for this case, PV equal to MRT, the R value will be 0.287 kilopascal meter cube over kg Kelvin for air. So for air, you have to use R equal to 0.287. For oxygen, you have to use different value. For nitrogen, you have to use different value. But all of them is can assume as an ideal gas. Okay, so in other words, you can see based on the R value, I know that pressure, I must use kilopascal. The unit must be kilopascal. Volume, the unit must be meter cube. Okay, M is a mass, unit is kg, and T is the temperature, the unit is Kelvin. So make sure you check the unit accordingly to this constant, gas constant R. Okay, and then let's come back to this PV equal to nRT. Actually, PV equal to nRT is the basic equation for ideal gas law. But we are rarely use this in Exergy. because the M here refers to the number of mole. Remember that one mole equivalent to how many molecule, but we not study until that extent. Okay, you can see that PV equal to nRT and PV equal to nRT. It's N and M. So what's the difference? The difference is in terms of R. They have a different value of R. You can see that this one, the R will be in terms of L. L refer to the volume. ATM refer to the pressure. 1 ATM equivalent to 100 kilopascal. And this, I think, refer to L is liter volume. And then K is the same temperature. And N is a mole, M-O-L. Okay, maybe it can be in terms of Joule, K minus 1, mole minus 1, same thing. Okay, so I just put it here, PV equal to nRT, which is the basic equation for ideal gas law. But mostly we will use PV equal to nRT, which we use the max, which is mostly our concern. Okay, and these R have also the relationship with the Cp and Cv. Cp and Cv is a constant, gas constant. Okay, we call it as a specific heat constant at constant pressure. If the process is a constant pressure, then we use the Cp. If the process is constant volume, then we use the Cv. But in general, when we use in the Exergy, actually it's just for you to know to find the entropy, the change of entropy delta S. Okay, this change of entropy can be calculated according to these three equations. You can use any of them, they'll give you exactly the same result. So we can use Cp ln T2 over T1 minus R ln T2 over T1. Or you can use the second one or third one. The only thing is depends on what information you have. If the question gives you Cp and R, then you use the first one. If the question gives you Cv and R, you use the second one. Okay, and then if the question gives you Cv and Cp, you use the third one. But of course, this Cp, Cv, and R is converted. You can convert from Cp to Cv and R. But as long as you have two of them, then you can get the third one. Okay, this is to calculate the entropy, which refers to the irreversibility or disorderly. How disordered and how bad is the condition. Okay, and then U refer to the internal energy. So delta U refer to the change of internal energy. We can use Cv dt. Cv refer to the specific heat capacity. Okay, and then dt is the change of temperature. Remember, always use Cv because the internal energy change is only referred to at the constant volume process. Always Cv. And then the last one is the delta H. The H here refers to the change of enthalpy, which is including the change of internal energy and change of the flow energy. Then you can have a value Cp delta T. You include the flow, so you use the Cp delta T. Okay, you no need to remember the equation. Equation will be given in the exam. Okay, and the exam will be open book exam as well, so don't worry about the equation. Just remember how to use it correctly. Okay, understanding the concept is more important than remember the equation. Okay, let's say we try this example. A 200 meter cube rigid tank contains compressed air at 1 megapascal. 1 megapascal, this is the pressure, and 300 Kelvin temperature. Determine how much work can be obtained from this air if the environmental condition is 100 kilopascal and 300 Kelvin. So 100 kilopascal is the atmospheric pressure, and 300 Kelvin is also the atmospheric temperature. And you are given R is 0.287 kilopascal meter cube per kg Kelvin. Okay, so how to start? The first thing you need to know is you want to get the M. You can see that the mass is not given, but without the mass, I am not able to calculate the total Exergy I have. I only can get the Exergy per unit mass, but what if I can get the mass? It's better. Okay, so based on the PV equal to nRT, I want to get the mass. So mass equal to PV over RT. And remember to use R as the unit written for the R, kilopascal for pressure. So pressure, I just put 1000. I don't put 1 megapascal. I don't put 1 million. I put 1000 only. And volume 200 meter cube, and then unit meter cube, so 200. And then R 0.87287, and T must be in Kelvin. Kelvin 300 Kelvin. So from here, I'm able to get the mass of this system, the mass of the air that I have. Maybe you calculate and let me know the answer. We have 2322.88 kg. Okay, so this is the total mass that I have in this system. So the question asks about how much work can be obtained from this air. So how much work can be obtained means that they ask for the Exergy. How much total Exergy you have in this system? Okay, so you want to find the Exergy. So this is flow or non-flow. You need to know that this is a flow system or closed system. Anyone? Or do you think this is a flow or closed? Any flow you have in this system, like turbine is a flow system. Okay, compressor, pump is all the flow system. But how about this? Is a flow or non-flow? Don't know. Closed system. Okay, so this is the closed system, so that we have to use the equation for the closed system. So are you going to calculate Exergy change? No, but we just want to calculate how much Exergy you have in the system. So we use this equation, phi. Phi equal to change of internal energy, work done to the surrounding, irreversibility, kinetic energy, and potential energy. Okay. Okay, these are the full equations for the non-flow. Then the next step, we need to check is that all the terms available. Internal energy, do you have change of internal energy? Remember that change of internal energy is depends on the change of temperature. CV, delta T. So delta T is 0 for our case. You can see that the temperature is 300 Kelvin and environment also 300 Kelvin. So it means that the work done cannot become from the change in temperature. So the change of internal energy, 0. Okay, the next one, work done to the surrounding. Do we have this? I think yes. Okay, or no? What do you think? Can this work done to the surrounding equal to 0? We don't know yet, so we have to put it. Okay, not stated anything, so we have to consider. Okay, and then the next one is the irreversibility. This is definitely available. None of the process we don't have this kind of irreversibility. And then kinetic energy and potential energy. From this question, I do not have any idea what is the kinetic energy and potential energy. So both of them can be 0. So I just need to consider two terms, which is the work done to the surrounding, and then this is the irreversibility. Okay, so first I have to calculate the work done to the surrounding. B 0, V minus V 0. Okay, so B0 is the pressure of the surrounding. I have it 100 kilopascal, so I don't need to do anything. But volume and the volume of the surrounding is an issue. I don't know. But I know that PV equal to MRT. Okay, so let's say we calculate per unit mass. Mass is 1 kg. Okay, I will just take mass as 1 kg first. So after that, we get the total exergy per unit kg, and then we only multiply with the mass that we get just now. Okay, so if m equal to 1 kg, I can get the V equal to RT over P. Okay, so I can write down V will become RT over P, which I have the RT and P. And this one is maybe I can put it one first stage, initial stage. Okay, so R do not have any stage because R is constant, always 3.287, T1 and P1. And minus V0, also the same thing, R T0 P0. So from here, I should be able to get the work done to the surrounding. Okay, so P0 is 100 kilopascal. I put 100 because we need kilopascal. We need kilo. I remember that the answer later will be in terms of kilojoule per kg. So everything in kilo. So R 0.287, T1 300, and P1 1 megapascal. So 1000 minus and this is P0, environment 100. So from here, you can get the work done to the surrounding. Okay. So I get negative 77.49. We get negative because you walk down to the surrounding, you are wasting the energy. Okay, so we just, if you get positive, you just put positive value. You get negative, you just put negative value. Just put it there first. Later we combine. Don't simply change it. Okay, so the second terms we need to get is the irreversibility. T0 S1 minus S0. So T0 S1 minus S0. So from here, I can get it from this one, delta S. Okay, so T0, I can get it from delta S. Let's say I use the first equation, Cp ln P2 over T1 minus R ln P2 P1. So the first term is T naught. T naught remain, you write in T naught. And then next one, you have to put the Cp ln T2. T2 over T1. Now it's 1 and 0. So it should be T1, T0. Okay. And then second term is R ln P2 over P1. Will become P1, P0. Okay, yeah, because it depends on this S1 and S2. If S2 over S1, everything will be 2 and 1. If 1, 0, everything will be 1, 0. then I will guess this. But I do not have CP, the problem. Okay, Samuel, T0 refers to the temperature of the surrounding. Yeah, I think T0 and T1 have the same value for this case. Environment temperature 300 Kelvin, and then tank temperature also 300 Kelvin. Okay, but remember that this is T0 environment and this is T1. Okay, so for this case, okay, yeah, Samuel, you get what I mean?
Okay, sir.
Okay, good. Okay, then we continue with this equation. Next, T1 over T0, both are 300 Kelvin. Can I say that ln 1? What's the answer for ln 1? Ln 1 equal to 0, right? So that this term I can completely equal to 0. So I left over T0. T0 is 300 Kelvin. Then R, R is 0.287. And ln P1, P0. P1 is 1000. P0, 100. And then from here, I can get TO S1 minus S0. Okay, so we have this term, and then I can substitute into the equation for 5. So P0, P minus P0, I have negative 77.49, and minus T0 S minus S0, I have negative 198.25. So the total I have is 120.76 kilojoule per kg. Okay, and this is the Exergy I have per unit kg. And remember, just now I get the mass is 2322 kg. So I can get the total work done, maximum work done, X, by multiplying this Exergy per unit kg with the mass that we have just now, which is 2322.88. So the final answer will be 280.5 megajoule. Okay, we do it step by step, find it one by one. And very careful on the positive and negative sign. Don't confuse. If you get negative, definitely you have to put the negative. And another thing that you need to take care of is 1, 2. Remember there will be 3 different stages: initial stage, final stage, and the death stage. Initial stage, we put it at 1. Final stage, we put it as 2. And the death stage, we put it as 0. Okay, and if the first term is 1 minus 2, the second, third, and fourth all must be the same, 1 minus 2. It won't be the first one, 1 minus 2, first stage minus second stage, and the second one is the balik and become 2 minus 1. No, not that case. So you have to check carefully. Everything must be consistent. Okay, so I think remember that it's easy to make mistake in this way. Okay, first question done. Don't worry, we have a lot of example we can try so that you can be clearer on the application wise. Any question on that? Okay, good. Then we can move to the next one. A coal-fired furnace is used in power plant. It delivers 5,000 kilowatt at 1,000 Kelvin. and the environment is at 300 Kelvin. Okay, so this is the total energy supply, or we call it as an input. And this is the temperature of the input, and this is the temperature of the surrounding. So what is the exergy of the added heat? This is the total energy, but how much exergy you have. So for this case, we need to calculate the efficiency. What's the maximum possible output, which refer to the exergy? Okay, so exergy should be equal to first law of efficiency for reversible process, multiply the input power. Okay, so for this case, we have first law of efficiency for reversible process is 1 minus d low over d high, and multiply with the 5,000 kilowatt. Then you will get this 3 over, so 0.7. So 3,500 kilowatt. So this is the exergy of this added heat. Okay, input is 5,000, but the exergy only 3,500, just because of the environment temperature of 300 Kelvin. Then determine the maximum percentage of the heat that can be converted to work, and maximum possible work percentage of the heat can be converted to work should be this efficiency. So only 70% of the heat can be converted to work. Maximum possible is only 70. And then the maximum work possible also, the Q max should be equal to the exergy, 3,500 kilowatt. Okay, so exergy will be equivalent to the maximum work possible. We calculate from the initial state until the that stage, or the environmental stage. Okay, this question very simple. Okay, then question 2.5. Oxygen gas is compressed in a piston cylinder device. So first check what is this device. Piston cylinder. So automatically it will tell you this is the closed system. Okay, and oxygen gas is a ideal gas. And then you are given the initial stage of 0.8 meter cube per kg. This is a specific volume and temperature, and final stage of 0.1 meter cube per kg and 287 degrees Celsius. Determine the reversible work input and increase in the exergy of the oxygen during the process. So actually, you can see this question asks two things: reversible work and increase in exergy. Actually, they are equivalent. Okay, reversible work should be equal to the exergy change. Okay, so it means that you only have one answer for this. So you have to find the reversible work of this. By this, you have to find the change of exergy from stage 1 to stage 2. How much actually it changed? Okay, I think it will take quite some time, maybe 10 minutes and more. Maybe you can continue on Wednesday. Any question before we dismiss? Okay, good. I think not too difficult. Can follow. Okay, then if there's no question, that's all for today. Thank you for your time, and see you coming Wednesday. Bye bye.
Thank you, sir.
Okay, bye bye.
Thank you, sir.